I'm going to talk a bit about the limitations on the ISO standard. Well, a lot of topics have been covered already, so there might be some repetition in what I'm going to say, but I'm going to say it anyway, so it gets you fresh in the head. So basically, this is a screenshot of the standard. And it has been said before how the outlook of this is. Let me just put on my pointer. So basically, we have a light source here. Then we have a aperture, and this aperture is being imaged by a lens. So we create a parallel beam. Here we have our sample. The parallel beam is reflected or scattered depending on the surface roughness of the material that we want to measure. And so we have this here is the incident angle, which has already been said can be 20, 60 or 85 degrees. And then we have a, let's call it a receptor lens, and it is focusing basically onto this plane here, where we have our detector field stop. And it's specified in the standard what the detector field stop sizes can be. And then basically after that one, we put our detector, so it just measures the amount of light coming from the sample. What I will talk about in this presentation is what we did. We did some ray tracing simulations to test theoretically what different gloss values can be measured if you take into account the tolerances which are specified in the source image aperture and the receptor aperture. I only did these tests or these simulations for the 60-degree geometry. Basically, it's a standard geometry, the 60-degree geometry. First, if you have a sample, you would test it at 60 degrees. If it's a gloss, or if the reported gloss value is lower than 10 gloss units, you would measure at the 85-degree geometry. If it is higher than 70 gloss units, you would measure at the 20-degree geometry. So basically, the 60-degree geometry is the one that you would always have to measure first. So this is the one I simulated. And this is an overview of how the simulation looks. It is a cross section. And actually this work, I should state this, it was done during a previous project. It was an Euromed project, BIRD project, in which some pre-normative work was performed to clarify how measurements on standard materials and surfaces, which have, for example, goniochromatism, sparkle, and gloss, how these measurements should be performed. So on this slide, you see the schematic overview of the ray tracing model, in which we have defined the rectangular source here. Basically, in the standard, it says that you have a light source and a source aperture. In our simulations, we changed this to a rectangular source, basically because then in our simulations, we can do important sampling towards this lens here, so that we are effectively only tracing rays which are going to this source lens. This allows for more efficient ray tracing simulations, basically. The source lens is a off-the-shelf lens that you can get from Edmund Optics. Then here you have your sample positioned, and then at the other side, we have our receptor lens, also just an off-the-shelf lens from Edmund Optics, which we can easily import in our ray tracing software. Both of these lenses are plano-convex lenses. And what you can see in this figure here is that we have a black reference style. So we only have Fresnel reflections, and we have this parallel beam, which is being focused onto where our detector aperture is. And then behind this here, this green area is our detector itself. So also we put some baffles here. It's to minimize stray light, because of course, if there is scattering here, light will also go next to this lens. So we want to eliminate that one as well. Also, yeah, I put in these numbers here in this simulation. We have a magnification of the image here of around 1.5. And then based on the, so in the previous section we had or in the previous slide we have a cross section. But in fact, in our simulations, we have adopted 3 different detector apertures. So we have a minimum size, a nominal size, and a maximum size. And these are defined based on the tolerances which are given by the standard. We do the same for the source size. So also there in the standard, there are some tolerances defined. So we have a minimum, nominal, and maximum source. And then to do a calibration, let's say, of our simulation, we position a reference tile, which is a refractive index as stated in the standard for a given wavelength. And we say that if we perform a ray trace simulation at this or with this sample in place, this is equal to 100 gloss units. So if we then want to determine the gloss units of a random sample that we put in place in the simulation, basically what we do is we just multiply the response of the detector with a sample in place to the response of the detector with the calibration tile, and we multiply it with 100. And then you get the gloss units of your sample. And hopefully this will work. I'm going to switch to the simulation first. So normally you should now see the simulation that I have made. It's made in TracePro, which is a commercial ray tracing software. And basically, if I zoom in here, you can see 3 different cubes, and the front surface here is the source that we are using. So it's the minimum source region, the nominal one and the maximum one. And then if you zoom out, so it's all at 60-degree angle. This is your source lens. We can put a sample in place. Then we have our receptor lens, a baffle, and then this is the detector aperture. And if I zoom in on this detector aperture, again, you can see different sizes which correspond to the minimum, nominal, and maximum size of the aperture as stated in the standard. And then behind this green square is your detector where we will capture the reflected light from the sample. So if I would perform a ray trace, let me just do this quickly. Yes. And then, so now the black tile is in place. And if we only look at the rays going to our detector, for example, if I would display all the rays, so you see this nice image of all the light only going to this source lens, to the sample. It's being reflected due to Fresnel reflections on the first surface of the sample. The second surface is a black 100% absorbing surface, and all the light is going through this detector lens, is then being focused onto this plane where your detector aperture is, and then of course captured by this detector here. So that's basically how we do the simulations. So this simulation, the resulting incident flux that we can collect here on our detector surface. So this value that you see here, this total flux, is basically what we will be using as 100 gloss units, and use it as a scale to determine the gloss units if we put any other sample in place. So with all these things in place, the simulation is in place. Of course, what we need to do now is we need to have a sample surface model. Sample surface model has been discussed a bit before in the previous talks. So we can do Brdf measurements, and a Brdf stands for the bidirectional reflectance distribution function. And it basically defines how the light scatters from a given incident angle towards all angles. And typically it's been denoted in the spherical coordinates. So you have the theta scatter angle, the phi scatter angle, and then you have your incident angles, and also you have your wavelength. So what we can do at our laboratory is we have an absolute spectral BSDF measurement device, so we can measure in reflectance and transmission. We are using a broadband light source, which is non-polarized, and the divergence of the incident beam, which is here, is around 0.1 degree. And then on the detector side, we have a spectrograph and a CCD, so we can measure across the whole entire visible wavelength region. And then for the angular coverage that our detector can reach, we have almost a full angular coverage, and we can move the detector in steps of 0.1 degree. We also have a very high dynamic range due to the fact that we can adjust the integration time of the CCD and also introduce neutral density filters in the optical path of the collimated beam, which is hitting the sample. So this allows us to measure, if you have a very reflective surface, you will have higher reflective values or high Brdf values in the specular direction, but away from the specular direction, you still might have some scattering, and we can still detect those that scatter at the off-specular angles. So these are measurements that we did on NCS samples. Frederick already said it, these NCS samples, they are defined as having a certain gloss unit. So we measured the NCS sample 5, 6, and 7. Those were white NCS samples. And we measured them at an incident angle of 60 degrees. So what we did was a single scan in the plane of incidence, and then to model the Brdf, to put it into our simulations, we assume that there is a rotational symmetry around the specular direction. But what you can observe from these measurements is that NCS 5 is more matte than the NCS 7. So the NCS 7 is, in this case, from the 3 samples, the most glossy sample. And what you can see is that the Brdf starts to become smaller angularly, but also the peak value increases. This is typical for the more glossy a sample gets, the specular or the narrower this peak will be, this profile will become, and the higher the peak value will be. Of course, we have to import this into our ray tracing model, so we have to do some, let's say, interpolations and translations to the coordinate system that the ray tracer is using. And this ray tracer is using this particular coordinate system. It's called the Harvey-Shack coordinate system, which is shift invariant. And this is how it looks like. It's a bit complicated, but basically you have your incident beam, you have your specular direction, depending on the incident angle, of course, and then you have a scatter direction, which is this vector D. And then if you project this vector onto your sample surface and your specular direction vector also on your sample surface, then you can have this distance between this local coordinate origin and this point here of your projected scatter vector. So this distance is one coordinate, and then you have from the local coordinate system this azimuthal angle, which is a second coordinate in the coordinate system. So when we import this into our ray tracing model, we can do again simulations and see what the incident flux on our detector is, and then calculate the gloss units. And we have done this for all the 3 different detector sizes, which are stated in the standard, taking into account this tolerance. So we have a minimum, nominal, maximum detector. And also for the source, we have a minimum, nominal, and maximum detector source size. So basically, we have 9 simulations for each of the 3 samples that we characterize the Brdf for, imported into the ray tracer. And what you see here is that we have maximum differences here, for example, for the, let's say, semi-glossy sample, the NCS5 sample, we have a maximum difference of 1.5. And the more glossy the sample gets, so going to NCS6, NCS7, the more glossy the sample gets, the less the maximum difference is between the gloss units we calculate, depending on these tolerances of the detector and the source. And this seems quite logical, because if you think about this, well, the more glossy a sample gets, the more narrow the Brdf profile becomes. So the less of an influence you will have from different sizes in detectors, because the whole beam or most of the reflected beam will still go through the aperture of your detector. So this makes sense in some way. But then we said, okay, we have this model in place. We can also do all kinds of stuff now. And what we did was we used some Brdf models. For example, this is quite a simple model actually. It's a cosine to the nth model. So if you vary the factor n, the larger it gets, the more narrow your Brdf profile will become. So for example, this gray line here is for a value of 2500. You will see it becomes more narrow than if you use a value of, let's say, 500 here. And for our simulations, we just calculated these Brdf profiles with this function, but we kept the total reflectance to 10%, so that total reflectance of all the samples is exactly the same, but just the Brdf profile changes. And again, we assume a rotational symmetry around this specular direction of 60 degrees. And then here, what you see is you have a completely different story in the fact that the gloss values, they change. They go from 40, let's say, up to 66. But we see almost no difference in this maximum difference. So for all these models, the maximum difference in gloss values is higher than 2 gloss units. And if you compare this one, for example, we have an average gloss value of, let's say, around 65. And we go back to the previous slide. Here we also have a nominal gloss value of around 65, but the difference, the maximum difference between all these tolerances is only 1 gloss unit. And here we have a difference of 2 gloss units. So yeah, it seems to be not only dependent on well, the width of the Brdf profile, but it's also dependent on the shape of the profile. In simulations, we can do everything we want. And this is something which is not in the standard, but we were thinking, okay, let's say that if you would shift your receptor aperture in the incidence plane or out of the incident plane, so parallel and perpendicular to the incident plane by 1 millimeter, what would happen to your gloss values that you report or that you can measure? And what we see is that, so we go from, this is what we had before, if it's in the exact position it should be, but just changing the sizes of the apertures. Then if we move it out of the plane by 1 millimeter, you see that these nominal values, they stay quite the same. We still have the same nominal gloss values, so these are comparable. And these maximum differences are also comparable. But if you change it in plane of your incident angle, then you see that the gloss value or the nominal gloss value changes quite a lot. You have a difference of around 3 gloss units. So this means that with these tolerances in place, if you would shift your detector by 1 millimeter, it already makes a large difference. So if you look at commercial gloss meters, one could expect that if they don't position these apertures quite perfectly, then you can have such a differences, which is basically what Fredrik also saw when he did the study and comparison between the different gloss meters. You can have large differences between different gloss meters, just basically because the apertures are positioned in a different position slightly, or they are maybe a little bit smaller or larger. It does make a large difference. And then, of course, what we did was using a ray tracer, a commercial ray tracer. Not everybody has the access to this kind of ray tracing simulations. But there's this paper which was published in 2005, and it's on estimating gloss from surface roughness parameters. And there's also a website where you can go to, And then what you can do is you can fill in your surface roughness parameters if you have them from a certain sample. You can select your angle at which you want to illuminate the sample, and then your collection angle. And if you change this, you can change all these parameters just on the fly. And if you change these parameters, you will see that the gloss value which is reported will also change. So this is something you can do if you have some time, and just investigate this a bit more. But my conclusion, or what I want to say here, is that all these tolerances, that as they are specified for both this detector and a source aperture, they influence what we are measuring. We want to measure specular gloss units, but it seems that these tolerances, well, or the gloss units reported, the deviations that you can expect are dependent on the Brdf profile of the material surface. So I think that the standard should not include these tolerances, as these do not correlate with the tolerances on the measured specular gloss units. So an idea would be, or it's just a thought, but a manufacturer should state what their aperture sizes are and how they are deviating from what it should be. Or you can have, for example, this maybe a test bench. I saw that at NMI levels, we have these gloss reference setups, so that we can measure maybe the gloss units for a set of samples which have all different Brdf profiles, and then see if you put a commercial gloss meter in there, measure these, let's say, reference set of standards, what their deviations are from the ones being measured at the NMIs. So yeah, this concludes my talk. And yeah, I think there are also some people from the industry present. So I think for people from industry, it's interesting to see that there are, or there can be, large differences in gloss meters. But it's basically just how they are built. And I think the standard is now lacking on a very, I mean, the tolerances, they should not be there. They don't make sense to me.